Good morning, everyone. My name is Jason Knapp. I'm the Chief Science Officer at Riverain Technologies. And today's talk is going to be about how we can use data synthesis and deep learning together to build more reliable AI systems in medical imaging. First, a little bit about Riverain. Riverain is a chest health AI company. Our applications are used across the globe in many different countries. And we have many approved, FDA-approved devices that we'll cover here shortly. So we have two main product suites broken out by modality. One is CT, clear read CT. In this, we have a dedicated lung nodule system that does everything from advanced visualization to automated detection and segmentation and tracking of lesions over time. It's a platform that's rapidly growing, adding new features and product extensions. Likewise with X-ray, we have an array of FDA-approved systems that does advanced visualization, detection, and even prior comparison. So today's talk is going to be about how we can use data synthesis and deep learning together to build better systems. Deep learning, as for those of you who may not know, is the modern version of neural nets. So a neural net is just a model that makes predictions. The way you build these neural nets, you tweak parameters until you get a satisfactory result on a training data set. In the past, when neural nets were used during the CAD era, the overarching concern was making sure you didn't over-tweak the model parameters so that you didn't so-called overfit. But today, the concerns are much deeper. So what have we learned in the last 5 years? Well, in the last 5 years, I think we've come to appreciate that radiologists' jobs are not in jeopardy, but rather the use of AI to build software for repetitive tasks is, in fact, a thing that is happening and is going to continue to happen. The other thing that we've learned as an industry is the importance of domain knowledge. So many of the early entries into AI from different domains, I think, mistook success in one domain for the ease of which it could be achieved in medical domain. And this, I think, led to quite a few false starts. One particularly culprit worth pointing out is this idea of weak supervision. So the idea that you can just hand an image to a model and say that there's some disease in it. That's called weak supervision. That does not work particularly well. So if you needed one reason why so many breakthroughs over the last 5 years have disappeared, this is pretty high on the list. And other things where, why did the AI make this choice? So an early idea was that you could show heat maps and that would be an explanation. That turns out not to be true. So what's required? So we need these complex models. We need large models because visual perception is a difficult problem. But complex models require lots of data. The other aspect in medicine that is particularly challenging is the devices themselves. So if you build an AI for one device and you apply it with a different device, depending on the application, you can get substantially different results. And even today, every few months, you'll see a paper or a article about how an AI has failed when it went from one area to another, even FDA-approved system. So it's still an outstanding problem. The other thing I think is perhaps the most important point of the talk would be that data is more important than models. So if you look at the work that's been done, a lot of emphasis has been placed on the models. But in fact, the most important thing with regard to getting a successful application is the data. And lastly, it's important not to take our eye off the ball. So the patient privacy and data concerns is a real issue, and it has to be sort of always kept at the front of one's mind when you're doing this process. So what does it take to sort of build intelligent systems in medicine? Well, one area that has to be tackled head on is this problem of acquisition. So like I said, for over 20 years, this has been a recurring theme. Radiomics works in the lab, but then it doesn't work in the field. I have a very successful AI model. I try it at a different hospital, it doesn't work. And so the principal reason for this is largely due to acquisition effects. So yet, we still want this power of deep learning. So we don't want to give up these powerful models. So in our view, the way to do that is to build the data and to train the model. Lastly, when these models make mistakes, it's important to have a pathway to make improvements that make sense. And we'll cover that toward the end of the talk. So a little bit about what happens under the hood at Riverain. So one of the unsung heroes, I think, of the last 5 years that never really fell into the hype bucket was the use of deep learning to address image acquisition, in particular image restoration, so denoising scans and so forth. At Riverain, we build this in upfront. So what we do is we do what is called normalization. So if I have a single patient that was acquired at different time points, and perhaps with different scanners and different protocols, the very first thing we do in our systems is to factor that out, so to speak, so that the resulting image looks as if it came from the same scan. And that doesn't include small changes, but rather substantial changes. So ultra-low dose scans are converted to high-quality looking scans. Fixed section CT scans are converted to thin section CT scans. Again, this is all done in preparation for what would be considered sort of downstream applications. And the same thing holds for X-ray. So in X-ray, we have the same exact process. The same patient, different acquisition device, go through normalization, get the same result. And this is absolutely critical if you're going to run your applications out in the world across different devices that you will never see. You will never be able to collect enough data to where you can train through that, so to speak. So as I said, data synthesis is a thing you can do. You can synthesize all variety of different acquisition effects and understand how the AI behaves and act accordingly to factor those out. So here's a quote from Richard Feynman. So this idea that what you cannot create, you do not understand. And I think this captures well the idea of data synthesis. So build the data that you need. And what you do when you're able to construct your training data set for models is you leave all this real data for validation. So another thing that plagues AI is weak validation, using a significant number of cases and leaving very little cases left to actually validate your model. So you're going to see this more and more and more, not just in healthcare, but in other sectors. So autonomous driving is another one. So Tesla Motors recently gave a demonstration where they're using a substantial amount of simulation to train their system. And the reason is this phenomenon here. So you have a typical problem where most of the data looks the same, but then you have a large range of variation. And what happens with AI is it gets very good at the bump. Okay, and so when you then apply it to these sort of variety of different scenarios, it fails. And that happens because, in part, AIs are trained to minimize average error. And so this predominant data actually makes the problem harder. So that the fact that most of the data is easy makes the problem more difficult, which is somewhat paradoxical. So to build a framework where you can actually construct the data, you address a whole host of issues. The problem of sample complexity. You have a whole variety of different images. How do you know how you perform? If I pull a book off the shelf and I find a very complex lesion, how do I know how our system will behave? If I can construct that example, I will know. So in our mind, data synthesis solves a whole range of issues, including the idea of continuous improvement. So here's just a sampling of what we mean. So I go off and I construct random nodules, synthesized. And so the motivation here is to cover the whole spectrum of disease. And this is just a fraction of what one could find. And if I go off into the world and collect a bunch of data, most of those nodules will look the same. And that, again, that plagues the AI when it comes to generalization. So another really core point here is that when you build synthetic data, you get perfect information. So I know this is a ground glass by construction. And I know that this is a part solid by construction. And so one of the challenges here is that it turns out for even clinical experts, this is a very difficult problem. So if you ask 10 experts, you might get a 40% agreement about what type of lesion it is. So if you were to train AI with that data, you would inherit the same biases. So what happens when you can synthesize the data, you get an enabler. So what you're looking at here is examples of real lesions and the output of what we call vessel suppression, which subtracts out normal anatomy and leaves nothing but the lesion itself. And as you can see, it's even able to sort of remove superimposed vessels and ground glass, yet importantly preserves the solid core and part solid nodules. And without data synthesis, it's hard to imagine how one could achieve this. Okay, the level of labeling that would be required is too meticulous, too time-consuming, so it wouldn't happen. So with data synthesis, you can build things that do more than just generalize well. You can build whole new types of applications. Likewise with chest x-ray. I mean, where is the problem difficult? The problem is difficult where there's most complexity. So in chest x-ray for nodules, that would be the apices. So to build a successful bone suppression, this is something we had to have. And what it enables you to do, again, this is a real lesion, very subtle, but yet the AI is able to find it with extremely high confidence and great fidelity. It's because it's seen this type of scenario many times. The last point here, and perhaps the most important point, is what do you do when you find a mistake? So you put an AI into the world, a doctor finds a false negative, they provide you this feedback, now what? Well, typically what one would be left to do would be to take that example, train on it, perhaps do some manipulations to it, and then apply the model again. And the statement that we won't miss it next time is sort of obvious, right? So you just trained on it, you've just memorized the example, but you haven't fixed the problem. So if you have a simulation engine, what you can do is you can try to hypothesize, why did the model miss this? And you can create an array of examples and test those examples. And once you find the core issue, you actually fix the problem, not the example. And so in our mind, this is perhaps the only principled way to address these issues and deficiencies of AI. So in summary, AI has to be device agnostic. It's going to be, whether you have disclaimers on your device for labeling or not, it doesn't matter. People are still going to apply it to different devices. This problem has to be solved. We think data synthesis, both for the purpose of factoring out device-specific characteristics and also addressing the problem of disease detection, is the core way to do this. And data is more important than models. So lastly, I should say that we're all in on this approach. We think it is the best way to do this problem. We think it's what ultimately leads to safe AI, and we're rapidly applying this to different areas. So whether it's pneumothorax or various types of cardiac disease and CT, it is working, and we are continuing to apply this. If you'd like to learn more about this, we have a second talk coming Wednesday where we'll come down and show some of our new applications, things above and beyond nodules. So thank you for your time.